Today we're going to talk about 3.6, and we're actually going to probably take a couple days on 3.6, but I plan to record the whole thing as one lesson here, so that you can watch or rewatch, kind of whatever you want to do. But we probably will spend a couple days on it because it is a rather large section. So here's your bell work. Go ahead and pause the video so you can work through this bell work. Okay, now that you've attempted this bell work here, we are going to work through it. And what we're going to do here is we're just going to graph this parent function. And this is the parent function of a rational, okay, 1 over x. So it says use a table of values here. So we're just going to put some x's and y's. And we'll just pick -3, -1, 0, 1, and 3. We could pick more if wanted, but again, this is f of x equals 1 over x. So when I take these x values and plug them in, I get -1/3, -1. 0 is actually undefined because it's 1 over 0. 1 over 1 is 1. And 1 over 3 is 1/3. Okay, so when we go to graph this thing out, we kind of have a unique situation here. Okay, so at -3, we're at -1/3. So maybe here at -1, we're at -1. At 0, we're undefined, which means we're not anywhere. And we're going to find out today that actually makes what we call a vertical asymptote. And at 1, 1, and then at 3, 1/3. Okay, so if I pick more values, if I pick maybe a half here, 1 divided by a half would actually be 2. Okay, and if I do -half, I get -2. And I could keep putting fractions here. Like I could keep getting smaller and smaller and smaller. Well, as I keep getting smaller and smaller and smaller, these numbers actually get bigger. They grow. So it keeps going up this way. Okay, and we can actually never have 0 here. And as these numbers get bigger, the overall number gets smaller. And here in quadrant 3, they actually do the same situation. As I get smaller and smaller and smaller, closer to 0, these numbers get larger. Again, I can't have 0, so it actually has no y-intercept. And as these numbers go out here negative, the overall number gets smaller and smaller and smaller. So this is our parent function. So if we want to look at domain and range, the domain, what x can be, is actually anything except 0. So -infinity to 0, union 0 to infinity. The range, looking up and down the y values, is also anything except 0. Okay, so this creates a horizontal asymptote and a vertical asymptote. And this is our parent function. Just like with the other parent functions, I could shift this thing up, down, left, right, stretch, shrink. I can still do all that, and we're going to talk about that here in the coming slides. Okay, so chapter 3.6 is rational functions. A rational function is any function that has x in the denominator. Okay, and it doesn't have to be 1 over x, but it has to be in some fraction form with a variable on the denominator. Okay, you do not have to have a variable on the top, but you definitely have to have one on the bottom. and then this is just the parent function. You could have something like radical 3 over x plus 9. Okay, x is on the denominator. I got a fraction here. We're good. Okay, so our goal here is to state properties and graph rational functions. Again, this is a rather long, lengthy section. So we're going to spend some time on it. A few things to remember. We need to remember how to divide polynomials. That is long and synthetic division both. We're going to do factoring polynomials. So the unit we just the first section of chapter 3, that's still going to come into play. Some end behavior stuff. And our HBAK. The whole shifting, stretching, shrinking, all of that kind of stuff will also come into play in this unit. So it's helpful if you remember those items. Okay, so this is a parent function. They have their table of values here. They picked a few different numbers than we did. The red here is the overall graph, the parent function. And you notice they've listed out their end behaviors. Okay, there are several end behaviors. There's 4 of them on this graph, and we're looking at each one here. So here, this says as x goes to infinity, f of x goes to 0. Okay, it's as it approaches that number. Usually with the polynomials, we were just going to infinity and negative infinity. Now we're going to actually get to functions that go to actual numbers. Okay, here this is a little tricky. As x goes to 0 from the positive, okay, so this is 0 from the right side, from the positive side, and down here you'll see it says as x goes to 0 from the negative side, so that's going negative to 0, okay, or 0 from the left. Y goes to negative infinity, so it's going down. That's the end behavior. And here it's going up, so it's going to positive infinity. It's all about where is x going, and then where is f of x going. That's how we note our end behavior. End behavior is anywhere you're going to put an arrow. Okay, I'm putting an arrow here and an arrow here, one here and one here. Okay, so those arrows, we would have an end behavior because it keeps going on forever, and we like to kind of see where is it going. Well, here as x goes to 0 from the right side, y is going to infinity. It's going up forever. Now, vertical and horizontal asymptotes dictate your end behavior. Okay, so asymptotes are just they're not a magic. I mean, we don't actually graph them. Okay, and if we do, it's a dotted line. We'll actually put it on the graph, but you don't need to graph it. When you do it on a calculator or something, it doesn't actually graph the line, but it is a line that your graph approaches. Like if we look back over here, I can tell that there's a horizontal asymptote right here. Why? Because that's where my end behaviors are going. I know there's a vertical asymptote right here. Why? Because that's where my end behaviors are going. If the end behaviors weren't going there or weren't approaching that, it wouldn't be an asymptote. Okay, so for vertical asymptotes, okay, of the function f of x, if y approaches plus minus infinity as x approaches a from the right or the left. So this is saying that here's my graph. As x approaches this vertical asymptote, y is either going to positive infinity or negative infinity. Okay, and you can see that down here. As x goes to that line from the left, y is either going to positive infinity or negative infinity. It is changing this end behavior of this arrow right here. Okay, if I put arrows right here, it's changing, it's telling me where the end behavior is going. right here, as x goes to a from the left, so as it goes this way, the y is going down. It's going to negative infinity. So that's a vertical asymptote. A horizontal asymptote is a line y equals b, is a horizontal asymptote of the function f of x if y approaches b as x approaches plus or minus infinity. So now we're looking as x goes out here to infinity, y up and down approaches this line at wherever b is. And we can actually cross these asymptotes. Okay, we can cross these horizontal asymptotes, but your end behavior overall, it's going to approach this horizontal line. So here we can say as x goes to negative infinity, y is going to b, wherever that line is. It could be positive, could be negative, doesn't matter. And this thing could, you have some functions that go up here and then they bounce back and forth across this asymptote. But in the end, it narrows down to wherever that horizontal line is. And we're going to talk about how do I actually get that equation of the line? How do I get this equation, or how do I get the vertical asymptote equation? How do I actually get those? And we're going to talk about that here in just a second. So bringing back some of our transformation stuff, we have the actual function of rationals. So f of x equals a 1 over x minus h plus k. So we can still write the parent function, what it is. We can write the h, b, a, k, domain, range, domain, range. We can still write out all of that. Okay, our parent function is going to be 1 over x, that rational. H inside here, the opposite of h goes left and right, positive right, negative left. We are not dealing with b. Okay, b would be right here. And we can actually do a and b all at the same time. Okay, so a and b can be done using the same values. So we're not going to look at b here. A is still a vertical stretch and shrink. Still, if it's a fraction, it's going to shrink it. If it's a integer, it's going to stretch it. A negative, we'll flip it over x. Okay, and because it's kind of a weird image, if I flip over x, it kind of also flips over y, which is why we don't really deal with b, because of just the way that the numbers work and how the graph looks. It's kind of it has rotational symmetry, so that cuts out some of those movements from b into a. K is still up or down, so positive up, negative down. And then your domain and range, those also shift. If I move this thing up or down, my range is going to change. If I move it left or right, my domain is going to change based on those movements. Now, the hard part will be getting it into this form. Okay? It's not always going to be given to you in this form. In fact, it is highly unlikely to be given to you in this form. And so let's look at a couple of these where we may have to do some work to actually get it in the right form. Okay, so graph each rational function and state the domain and range. So this is pretty close to the form. The only thing here is this 2. So if I rewrite that as a 1, or if I factor that 2 out front, I have 2 parentheses 1 over x minus 3, and you could put a plus 0. Okay, so my HBAK, so we don't have a B, so HAK So h would be this 3. So we're going right 3. A right here. So we've got a vertical stretch by 2. And then we're not going up or down any. Okay, so when we go to graph this, I'll go ahead and graph the parent function here. Okay, so we're at 1, 1, 2, a half, 3, a third, 4, a fourth. So that keeps going down. And then a half, 2, a third, 3, a fourth, 4. And then -1, -1. And it's all the same points just in this quadrant. So we're half, we're at a third, we're at a fourth. A half is at 2, a third is at -3, a fourth. So we've got all of these points. I'm going to draw this dotted because that's my parent function. And again, we have these asymptotes. Okay, these asymptotes will help us shift things up, down, left, right. So if I trade back to red here. So if we just take this point 1, 1, we're going to go right 3. So 1, 2, 3. We're going to vertically stretch it by 2. So now it's going from 1 to 2. And then that's it. So we're not moving it up, down, left, right, any. Okay. So I got that dot there. Now, if I look at this horizontal asymptote, I'm not moving it. I'm not moving it up and down any. So this new red graph still has this horizontal asymptote, which means my end behaviors are still going to approach that y = 0 line. Now, we had a vertical asymptote at 0, but I moved everything right 3. So that vertical asymptote also gets moved right 3. So 1, 2, 3. Now I have this vertical asymptote here. Okay, so what's going to happen is this curve right here, this blue curve, the whole thing got shifted over. So it's still in this quadrant. We're still approaching these lines, but I vertically stretched it by 2. And you can see that right there. Okay, so if I take this point at 2, 1/2, I'm going to go right 3. So 1, 2, 3. Vertically stretch it by 2. So instead of 1/2, now it's going to be at 1. Okay, so I've got some points on here, and then we can graph this. So it's going to approach that one. We've got those 2 points. It's going to approach this one. And then these points also get moved over 3 and vertically stretched. So here I'm going to go right 3, 1, 2, 3, vertically stretch it by 2. So instead of -1, now it's at -2. And here at -2 1/2, so 1, 2, 3. And if I double the y values, it's here at -1. So then we have this graph right here. Now, it's kind of hard to see the vertical stretch or shrink, but you can base it on how sharp this corner is. If you stretch this thing out, this corner here isn't going to be as sharp. If you were to compress it, it would be a lot sharper. Now, the next one is definitely not as easy because I have a binomial here in the top. So in order to deal with that binomial, we're actually going to do the long division to see what's left. Okay, so we're going to take 3x plus 5 divided by x plus 2. So how do I make x become 3x? I multiply by 3. So then I get 3x plus 6. Do my subtraction. These cancel. 5 minus 6 is -1. So I get minus 1 over x plus 2. And you can kind of see this looks like the HAK form. If I rearrange things just a little bit, I have negative 1 over x plus 2 plus 3. Okay, so HAK is telling me to go left 2. I'm going to flip it. This negative says flip it over the x-axis and then up 3. So we can move the asymptotes first. So this vertical asymptote goes left 2. So 1, 2, and I am going to graph it on this same one. You don't have to if you don't want to. So that goes left 2, and the horizontal one goes up 3. 1, 2, 3. So now our origin is here. Okay. And again, I can take these dots and I can move them. Okay, if I take this 1, 1 here, I'm going to go left 2, 1, 2. I'm going to flip it over the x-axis. Flip it over. So now we're at negative 1. And then up 3. 1, 2, 3. So you can see instead of being in this top right quadrant, now we're in this bottom right quadrant because it got flipped over. And I didn't stretch or shrink anything. So if we kind of look at the numbers here, this is 1, negative 1. I would go 2, so 1, 2, a half. Or I'd go a half, negative 2. So I didn't stretch or shrink anything. So these numbers are still the parent function numbers. The vertex or the origin just got shifted over. Okay, so if I go from the origin here, that's minus 1, up 1. Because again, it was in the bottom left, but I flipped it over, so now it's in the left top. So that's negative 1, 1. This would be negative 2, a half, or negative a half, 2. And we would still be approaching those asymptotes, horizontal and vertical. So now we're looking at that. Okay, so I can use all of these transformations to help me get from the parent function to the other one. Okay, so finding asymptotes is really, really easy. Easier than what this slide predicts. So the vertical asymptotes of R lies where x equals a are the zeros of the denominator. Okay, so here's the important part. Vertical asymptotes are the zeros of the denominator. So if you factor out this denominator, that's going to give you some where the vertical asymptotes are. There's one caveat to that, and we'll get to that later on. But for right now, vertical asymptotes are where the denominator is 0. Okay, so you're going to set those, factor it, set them equal to 0. Horizontal asymptotes, and I could also throw slant asymptotes in here. All you're going to do is you're actually going to do the division. So divide. And you're going to look at your quotient. Okay, so whatever you have. Not the remainder part, just what comes out at the top. Okay, usually it's a line, but it could be a quadratic, it could be a cubic, it could be something else. Okay, these rules right here focus on if it's like a straight horizontal line. So this says if the degree of the top is less than the degree of the bottom, then it's y equals 0. Okay, so that's like if I have x squared whatever over x to the third whatever. Okay, the degree of the top is less than the degree of the bottom, so you have a horizontal asymptote of y equals 0. If you actually tried the division, you couldn't make x to the third become x squared. Okay, that's not how division works. So if you can't do the division, you would put a 0 there, and that's what you would have. If the degrees are the same, it says it's y equals your leading coefficients. Well, if the degrees are the same and you actually try to do the long division, then your one term up there at the top is going to be your leading coefficients over one another. If the degree of the top is bigger than the degree of the bottom, so if you have like x to the fourth and stuff over x to the third and then a bunch of stuff, there is no horizontal asymptote. And that's correct, but we're still going to find either the slant asymptote or the parabolic asymptote or the cubic asymptote. There are other asymptotes that you get based on actually doing the division. So you can figure out everything just by doing the long division. Okay, so let's look at some of this here. Okay, so graph this rational function and state domain in range. Okay, so we're going to look at the vertical asymptotes first. And the way we're going to do that is we're going to have to factor the bottom. Okay, so if I factor the bottom, I need factors of 1 that add to 2. That is 1 and 1. Signs the same, both negative, so x minus 1, x minus 1. So we have a vertical asymptote. This is on the bottom, so I know that x cannot be 1. So that creates a vertical asymptote at 1. So when we go to graph this, we can just graph a vertical line, dotted line at 1. Again, this dictates my end behavior. So as I come this way, I'm either going up or I'm either going down closer to it. As I come from the left, I'm either going up or I'm either going down. Okay, now to find the horizontal asymptote, I can actually just do the division. Okay, so we're going to say 2x squared minus 4x plus 5 divided by x squared minus 2x plus 1. If you don't want to have to remember all the rules, just do the division, and it will tell you what it needs to be. If you want to go through and remember each rule that it is, go and remember each rule. Okay, so here, how do I make x squared become 2x squared? I'm going to multiply by 2. That's all I have to do. The rest is the remainder, and I don't want the remainder. This asymptote, this horizontal or slant or whatever asymptote it is in the horizontal direction is y equals 2. So at y equals 2, I have a horizontal asymptote, which means as x goes to infinity, it's approaching this line. As x goes to negative infinity, it's approaching this line. It still may cross that horizontal asymptote, but it is approaching those numbers. Now, how do I know exactly where it is? We can plug in points. Okay. We can make a table of values and see, okay, is it going like this way? Is it going this way? Does it cross? What's it do? So in our table of values, you're going to pick a couple, maybe a fraction in here, maybe this number, let's see, that's 2, and then maybe 1.5, maybe 0.5, 0, -1, and 3. Okay, if you take those numbers and plug them in and see where you're at. So let's see, 2, when I plug that in, I get 5. 1.5, I get 14. A half, I get 14. So that's kind of interesting that we're on each side of the asymptote, but we're way up here at 14. Okay. 0, I get 5. -1. I didn't. Let's see if I plug that in real quick. So I get 2.75. Okay, so if I start plotting some of these, 2, we're at 5, so that's way up here. 1.5, we get 14, so that's way up here. So what this thing is doing is it's approaching there, and then as I go this way, it's approaching this line. And then over here at 0, we were at 5. At a half, we were at 14. So now it's approaching there, and then coming through here and approaching here. Okay, we can still get y-intercepts. We can still get x-intercepts. We can still get all of those things from the graph. Okay. Now, x-intercepts, I think, maybe I skipped that slide. X-intercepts come from, oh, here we go. So a little bit more into sketching the graph. So the first thing you're going to do is factor. Okay, you're going to factor the numerator, factor the denominator. Then you're going to find your intercepts. Finding the x-intercepts by determining the zeros of the numerator. Okay, so your x-intercepts, oh, I don't want that color. X-intercepts come from the top, the numerator. Okay, and the y-intercepts come from the value of plugging x in. Okay, you may not have any x-intercepts. This last problem we just did would have no x-intercepts. If I found the zeros for this, they would be imaginary. Okay, it doesn't cross. I could use the quadratic formula. They'd be imaginary. It doesn't cross the x-axis. So, so find your x and the y-intercepts. Y when x equals 0. Then you're going to find your vertical asymptotes. So you find the vertical asymptotes by determining the zeros of the denominator. So zeros of the denominator. And see whether y goes to infinity or negative infinity on each side of the vertical asymptote by testing values. So that's when we made our table of values, just to kind of see where things were. So find the horizontal asymptotes, if there are any, using the procedure described in the box. So that was on that box they're talking about is this box right here. So we can do the division and see what's happening. And then sketch the graph. If you need more points to plot, pick more points. Pick additional points as you feel need. That way you can see where the graph is actually going. Okay, let's look at one. So graph a rational function. Okay, so first we're going to factor everything. Sometimes the top or the bottom can't factor, but if we can, we're definitely going to want to factor it. So 2 times 4 is 8. Factors of 8 that subtract to 7 would be 8 and 1. So we can factor that. So this would be 2x minus 1 and then x plus 4. So you get your 8, your minus 1. Factors of 2 that subtract to 1. So x plus 2, x minus 1. Okay, so we've got everything factored. So your zeros, we need to find the step 2 would be to find the x and y intercepts. So your x-intercepts come from the top being 0. So x-intercepts are a half and minus 4. That's the top being 0. Your y-intercept is plugging 0 in for x. So if I plug in 0, this goes away, this goes away, this goes away, and this goes away. So you have negative 4 divided by negative 2, which is 2. Okay, so all that goes away. So you have your x-intercept and your y-intercept. Your vertical asymptote is where the bottom equals 0. So you have actually 2 vertical asymptotes at x equals minus 2 and 1. Okay, so then we go to horizontal asymptote. And if we actually just do the division, so 2x squared plus 7x minus 4 divided by x squared plus x minus 2. So how do I make x squared become 2x squared? I multiply it by 2. And then the next thing would be my remainder, so I'm done. So my horizontal asymptote is y equals 2. Okay, so now we can start plotting those 4 items out. So, all right. All right, so I have an x-intercept of a half and negative 4. 1, 2, 3, 4. So they cross there. A y-intercept at 2. So here. I have a vertical asymptote at negative 2. So we'll put that in a different color here. So negative 2 and 1. And then a horizontal asymptote at 2. Okay, now remember, horizontal, the asymptotes are where the end behaviors go. Okay, so you can see it right here. I'm crossing this. Okay, but this horizontal asymptote is what's happening out here as x goes to negative infinity and as x goes to infinity, not right here in this set of numbers. Okay, and then your vertical asymptotes are where the graph is approaching as it goes up and down. So I can see here right now that this dot is in this quadrant. So as I go this way, as I go closer this way, I'm either going to approach here or approach here. It's likely going to be down here. Okay, I would pick this point right here, plug it in, and see where I'm at. So if I take -3 and plug that and plug -3 in, I get -1.75. So at -3, I'm at -1.75. I'm down here. So that tells me that this graph curves down this way. And then as I go out to negative infinity, it curves to this line. It approaches this line. In here, I would pick -1 and plug it in. When you plug in -1, you get 4.5. So that's up here. And if you were to pick some other numbers in here, you actually see that this looks like an x to the third. So as we kind of come up here, x to the third there, and it curves back up. Okay, it approaches this vertical asymptote and approaches this vertical asymptote. Now over here, I have no idea. Is it above here? Is it below here? Where is it at? So that's where we're going to take 2 and we're going to plug it in. When I plug 2 in, I get 4.5. So we're up here. And it's going to model that behavior that it had over here. So as I go to the right, it's going to curve down this way and approach this line. And as I go to the left, as I approach this asymptote to the left, it's going to curve up and approach that asymptote. Okay, and you can check this with a table of values. Plug in some numbers, see where you're at. Okay, I expect to see some dots here from your table. If you use a graphing calculator to check yourself, I still want to see the dots. You're still going to have to find all of this information before you just go and graph it. All right, let's look at another one. Okay, so graph the rational function here. Okay, so again, first thing we're going to do is factor everything. So the top is a difference of squares. So you have x plus 2, x minus 2. And down here, it looks like we have got a greatest common factor. So factor out this 2x. And then you have x plus 1. Okay, so we want your x-intercepts. X-intercepts is where the top equals 0. So you have plus minus 2. Y-intercept. Plug in 0. So you get 0. That goes away. That goes away. That goes away. So you actually have 0 on the bottom. And you can't have 0 on the bottom. So there actually is no y-intercept. Okay, so you could write the word none if you wanted. Okay, so vertical asymptote. Vertical asymptote is where the bottom equals 0. So we got 2. So 0 and -1. And then for our horizontal, you're going to just do the division. So you have x squared minus, plus 0x minus 4 divided by 2x squared plus 2x. So to make 2x squared become x squared, I have to multiply by a half. And then the rest would be my remainder. So you get y equals a half. There's your horizontal asymptote. Y equals a half. So it actually goes up, shifts up by half. I think I forgot domain and range on this one here. So let's go back here real quick and state the domain and range. So the domain is what x can be. So start at negative infinity. It can't be -2, and then it can't be 1. So I have negative infinity to -2, union -2 to 1, union 1 to infinity. Okay, for the y value, we look up and down. So for the range, we're looking up and down. So I can have negative infinity, and then we're looking up. The only question here is at 2, because it doesn't cross here and it doesn't cross here, but it actually crosses here. So I can have 2, and then it goes to infinity. If you look at this middle section, you can have every y number here in this middle section. So it's actually negative infinity to infinity. Okay. All right, going back to this one, I think we have enough to start sketching this thing out. Okay, so your x-intercepts here are at plus and minus 2. And then there are no y-intercepts. And then, so you have vertical asymptotes at 0. So again, that's kind of why you don't have any y-intercepts, is because it approaches this line in whatever direction. And -1. And you have a horizontal asymptote at 1/2. So right in there. So you can kind of see we're going to be down here. So you might pick some other values here. Like if I pick 1, if I pick 1, I would be at -0.75. So here, so you can see I'm going to approach this horizontal asymptote right there, and I'm going to approach this vertical asymptote to negative infinity. And then here, again, we could pick this -3, or we could pick 2.5. We could pick some number in here. Let's say I pick 2.5. So I have 2.5 squared minus 4 over 2 times 2.5 squared plus 2 times 2.5. So it looks like we're at point. Oh, I need it. So 2.5 was right here. So somewhere up here. So as I go this way, we're approaching here. It was like right here. And then as I go this way, we're going to approach this way. So you can pick points closer to that x, to that vertical asymptote if you want. Now, the space in question is right here. Okay, so you're going to need to pick some values in here. If you want to put this thing into y equals and look at the table, and maybe you put in -0.1, -0.2, -0.3, -0.4. You put in some decimals in here and see where it's at. Okay, so x, y. Let's say we put in -0.1. -0.1 is 22.17. Maybe -0.3. -0.3 is 9.31. Okay, so 0.1, we're really high. So we're way up here. -0.3, way down here. So it's coming, so we're approaching this way, but does it come down here? Does it turn around? What happens? And you can look at your graph on your calculator to help you determine that, or you can just keep picking numbers. Okay, if I pick -0.5, I get 7.5. But if I go all the way to like -0.9, I'm back up to 17.72. So it does come down and turns back around. Okay, kind of a parabola looking thing in here. And we could find, you know, if you are on your calculator and you graph this, you could find this minimum. Second trace, calculate that minimum right there and actually put that value on there to be precise. And we're going to need that if we want to calculate the actual domain and range. Okay. So looking at this value, let's plot it here on a graph. And I know I don't have my document camera here to show you the calculator steps. But we're going to put it into y equals. We're going to graph and make sure that I can actually see the curve there. So you might have to hit zoom standard. And you can check your graph to see where we're at. And then we're going to calculate the minimum here. And make sure you're watching your X and Y values to see where you're at. You are between X being -1 and 0. Okay, it's calculating. So this point is actually about 0.5, 7.5. Okay. And that helps us for our domain and range. Okay, so domain. Okay, so we can have negative infinity. We can go all the way up to this -1 right here. We can't have a -1. So negative infinity to -1, union -1 to 0, because that's my next stop, and then 0 to infinity. Range, for the range wise, we can start all the way at negative infinity. And we can go all the way up to a half right there. So a half, because it keeps approaching that number. Union, and then I can come here to 7.5, and I can actually have that 7.5. So bracket 7.5, comma, infinity. So we've got that jump there, and you got to make sure that you understand the difference in having a parenthesis and bracket versus an asymptote or an actual dot there. Okay, we're going to stop here. I think this is enough for one day's lesson. So we're going to stop here. I'll give you some homework problems here on WebAssign, and then we'll continue on. We still need to talk about a few more graphing things such as holes and maybe some parabolic and the actual slant asymptote of things. But this gives us a really good foundation of graphing and some of their characteristics. So if you have questions, feel free to reach out. If not, I'll see you in the next video.